Welcome back. This video is going to go over section 1-2, fundamentals. So our learning goal for this section is to understand the fundamental concepts and principles of statics. So I'm going to start by going over the four basic quantities, and these are length, time, mass, and force. So length is used to define the location of a point in space. The point's coordinates define its location, and the coordinates are the lengths measured from the origin or some reference point to the given point in three directions, so think x and y and z-axis. Length allows us to describe the size of a physical entity. Time is a familiar concept where we can basically use our intuitive notion. So time basically tells us how long something will take. And in statics, the principles are independent of time, and we really don't use the quantity of time, but you will use it in dynamics. And mass is basically the quantity of matter. So we're going to use the concept of mass to compare the action of one body with that of another. So for instance, two bodies of the same mass are attracted to the Earth in the same way. Force represents the action of one body on another body and is generally considered as a push or a pull. So a force can be exerted by actual contact or through distance when the bodies are physically separated. We can classify forces as contact forces between two bodies that are touching, so for example, you leaning against a wall, or as long-range forces between two bodies that are some distance apart, and this would be your gravitational or magnetic forces. A force is characterized by magnitude, direction, and point of application, and we represent it with a vector. If you're not familiar with vectors, that's okay. We'll examine those in Chapter 2. And some common types of forces would include your gravitational force, think weight, force of tension, force of friction, and a normal or perpendicular force. Since a force is exerted by one body upon another, forces must be described as interactions. So one of the biggest mistakes we can make is to think of a force as something a body has. At least two bodies are needed for a force to even exist. So think of it this way. Body A acts upon body B with a force, or body A exerts a force upon body B. So you have to have at least two bodies for there to be a force. The basic quantities that we just went through, length, time, mass, and force, all have units, and we'll consider units in the next section. Now I want to go over a couple of simplifications. So a particle is a very small amount of matter that may be assumed to occupy a single point in space. And it does have a mass, but its size can be neglected because it's very small. Then we have a rigid body. So a rigid body is a combination of a large number of particles occupying fixed positions with respect to each other, both before and after a load or force is applied. So in other words, a rigid body does not deform or change shape when forces are applied to it. When this happens, this is great because then the material properties of the body don't have to be considered when we're studying the effects of force acting on the body. And then we have a concentrated force, and basically that's the assumption that a force acts at a singular point on the body instead of spread out over the body. Now we have Newton's laws of motion. So Sir Isaac Newton formulated three fundamental laws of motion in the latter part of the 17th century. So if you've taken a physics class, you're already familiar with these, but I'm going to go through them anyway. So the study of mechanics was established on the basis of these three laws of motion. Their validity is based on observational experience. And these laws apply to non-accelerating particles. So the first law states that a particle at rest or moving with a constant velocity will remain in that state unless it's subjected to an unbalanced force. So basically, if it's at rest, it will continue to be at rest. If it's moving with a constant velocity, it will continue to move with that constant velocity unless there's another force that unbalances it. If the resultant force, the sum of forces acting on a particle is zero, its velocity is constant. So let's say we have this particle or body here. So you have these two forces acting on it, F sub 1 and F sub 2. And maybe these forces are, 10 newtons each. See how they have the same line of action and they have opposite direction? Well, what would be happening with this body or particle? It's probably at rest, right? If we take this and we add an unbalanced force to it, let's call this F sub 3, then what's going to happen with this particle now? It's probably going to experience an acceleration in this direction. The second law, if a resultant force acting on a particle is not zero, basically you have an unbalanced force, then the particle will experience an acceleration. The acceleration has the same direction as the resultant force and a magnitude that is directly proportional to the resultant force. F here can represent the resultant force, and this particle or body is experiencing an acceleration in this direction. Mathematically, this law can be expressed as F equals ma. F here represents the resultant force acting on the particle, m represents the mass of the force, and a represents the acceleration of the particle. And the third law states that the mutual forces of action and reaction between two particles in contact have the same magnitude, same line of action, and opposite direction. So here you have particle A, particle B. Here you have force F and negative F. I'm using a negative here since they have the opposite direction. And you can see here that they have the same line of action, and then assume that they have the same magnitude. Newton's law of gravitation governs the attraction between any two particles. So mathematically, it states that the gravitational force between any two particles is given by this here. So F is the magnitude of the force, and it's equal to G times m sub 1, m sub 2, divided by r squared. G is the universal constant of gravitation. M sub 1 and m sub 2 are the masses of the two particles, and r represents the distance between the two particles. This law is basically an extension of Newton's third law because it introduces the idea of an action exerted at a distance when the two bodies are not in physical contact. So the action F and the reaction negative F are equal and opposite, and they have the same line of action. So here you have particle, some particle, call it particle A. Over here you have particle B. A has mass m sub 1, B has mass m sub 2. These are the forces, and r here is the distance between them. And you can see that these forces here have the same line of action. Weight refers to the gravitational force of the Earth on a particle or body located on or near its surface. Sometimes students will forget that weight is a force. It has a magnitude and a direction. So weight is equal to mass times acceleration due to gravity. And if you use the previous equation that we had gone over, I'm just going to put that up here. Just kind of relabel some stuff. You can let m, capital M, be equal to the mass of the Earth. Lowercase m can equal the mass of the particle. And r can equal the distance between the center of the Earth and the particle. So you get this here. And then let lowercase g be equal to capital G, m over r squared. When you do that, then this equation just becomes W equal mg. So the weight is equal to mass times the acceleration due to gravity. And this is how we can express the magnitude, W, of the weight of a particle of a mass m. And if you compare it to this equation from Newton's second law, you can see that the constant g is the acceleration due to gravity, and we'll either use g equals 9.81 if we're doing meters per second squared, or 32.2 if we're doing feet per second squared. Weight will be the only gravitational force that we consider in our study of mechanics. In this section, we went over the 4 basic quantities, we went over a few simplifications, and we went over Newton's laws. So now I want to go over a couple quick examples just to test our knowledge and make sure that we're comprehending this information well. So for example 1, we want to consider a block that's resting on a horizontal table. So for part A, which object exerts a downward force on the block? So would this be the book itself, the earth, or the surface of the table? And our answer is the earth. Part B, the downward force that acts on the block is a, well, what kind of force? So is it a contact force or a long-range force? And in this case, it would be a long-range force. Part C, what is the downward force that acts on the block called? So would this be tension, friction, or weight? And in this case, this would be weight. Part D, which object exerts an upward force on the block? So would this be the block itself, the earth, or the surface of the table? And this would be the surface of the table. And part E, the upward force that acts on the block is a what kind of force? Would this be contact force or long-range force? And this would be contact force, since the block is right on the table. And last question, what is the upward force that acts on the block called? So would that be tension, weight, or a normal, basically perpendicular force? And in this case, it would be a normal force. Think of it this way, you have your table, and here's your block on the table, and your table is exerting this normal force here. It's perpendicular to the block. Why don't you try to answer example 2 for me? So we have a string that's attached to a block, and it's used to pull the block to the right across a rough horizontal table. Don't worry about when you might come in contact with the scenario. Let's just try to answer these questions. So for part A, which object exerts a force on the block that is directed to the right? Would that be the block itself, the surface of the table, or the string? Very good, that's the string. All right, part B. The force that acts on the block and is directed to the right is a, would this be either a contact force or a long-range force? And the string is connected to the block. So this is a contact force. Part C. What is the force that acts on the block and is directed to the right called? There should be a question mark there. So is this tension, weight, or friction? Very good. That would be tension. Part D. What object exerts a force on the block and is directed to the left? So go back to your scenario if you have to. So would this be the block itself, the string, or the surface of the table? That's correct. This is the surface of the table. E, the force that acts on the block and is directed to the left is a contact force or a long-range force? Very good. Contact force. Thank you. And last question. What is the force that acts on the block and is directed to the left called? So would this be tension, friction, or weight? Perfect. Friction. Thank you. All right, so that concludes section 1-2. Try the homework problems, and then I will see you in the next video. Thank you for listening.